Hello everyone, welcome to our 10th webinar. This webinar is going to be on cone penetration testing, quality control, and quality assurance. Dr. Robertson is going to be the presenter. Feel free to use the questions section in the webinar control panel to type in your questions as we're going. I will write these down and we will have a question and answer period at the end of the broadcast for about 15-20 minutes. I will turn it over to Dr. Robertson at this time. Thank you.
Thank you, Kelly. Well, welcome everybody. As Kelly said, this is the 10th webinar in our series of free webinars, and this one today is going to be related to quality control issues for cone penetration test data. And just a reminder again that most things that we're going to see in the CPT guide, which is available for download from a variety of websites. And there's really two basic components when it comes to quality control. The first one is how do I get good CPT data? And for consultants, that's often focused on how do you specify the test, what standards, what are the key elements that you need to specify and check. And for contractors, it's what are the key elements related to equipment and procedures to make sure that the data is good. And of course, the second component is if you're given data, CPT data, how do you evaluate the quality? What do I do with what I have, and how do I evaluate, possibly correct and process the data? So just a reminder again of the basic components of the cone. Most cones measure two or three things. All electric cones measure the tip resistance, which is the load on the tip divided by the cross-sectional area to give you the tip resistance in units of stress. And then they also measure the sleeve friction, which is the load of the soil passing the sleeve, which divided by the surface area gives you the frictional stress. And piezo cones also include pore pressure measurements. So CPT-U includes pore pressure measurements, typically in this U2 location just behind the shoulder. And I've added to this slide a little picture of a cutaway section of a typical cone showing the strain gauge load cells, because we're going to talk about cone design, so it's nice for you to actually see what the inside of a cone looks like. So how do we get good CPT or CPT-U data? In general, CPT data is very reliable. I mean, that's why the test is so popular, because it is a generally reliable, repeatable test. And that's because essentially it's operator independent, so it doesn't matter who's doing the test, providing the equipment is maintained according to the standards, and the procedures are carried out according to the standards, and you get typically get good reliable data. But we will touch on issues about how do you ensure you get excellent data, and it's really an issue primarily when you get into very soft soils, because the measurements get very small, and so how do you ensure that you're getting the best quality measurements that you can in very soft sediments. But it's worth reminding ourselves that we're going to talk about issues related to quality control of the CPT, but it's good to keep in mind that in general this is a test that's far more accurate than the older tests such as the standard penetration test. So we're going to talk about CPT in soft sediments and the accuracy of the measurements, and of course one of the downsides of the standard penetration test is if you encounter a very soft clay, then it's not unusual to get a blow count of 0, where the sampler penetrates under its self-weight. And so in a way that's infinitely inaccurate, and so you have really no sense of how strong that material is other than the fact that it's soft. So the CPT is far better than the traditional methods of drilling and standard penetration tests, but there are some elements that it's useful to keep in mind about how to ensure that the data is as high a quality as possible. Given the ground conditions, etc. So for consultants, as I said, that's often focused on the specifications, and contractors, the equipment and procedures. So what standards are there? And there's a variety of them. The International Society of Soil Mechanics and Geotechnical Engineering have a number of technical committees. I actually chaired one of those technical committees. At that time it was called TC16, and we developed an international reference test procedure. so often has that acronym IRTP, International Reference Test Procedure, published in '99, then republished in 2001. In the US, of course, ASTM D5778, recently updated in 2012, some very minor updates added to it. And then in Europe, they have their Eurocode, and then they also have their series of CEN standards or ISO standards. And so there's a recent one that was also updated in 2012. And all three of these cover both CPT and CPTU with pore pressure measurements. And of course there's a number of national standards and codes, and the offshore industry in a way has their own standards that are often built around these ones above. They're built around the International Reference Test Procedure and the ISO one. So they're very similar, but offshore procedures tend to be a little bit different because the tests are referenced to the seafloor, and so there are some procedural elements of how they do that. That's worth noting. That it may come up later as a question, that when you do overwater CPT, everything is referenced to the seafloor or the bottom of the river or the bottom of the lake. And the reason for that is because the effective stress in the soil is zero at the seafloor, so it's independent of the depth of water. And since soil behavior is controlled by effective stresses and it's zero at the seafloor, then everything is referenced to the seafloor when you do overwater work. So some of the key elements of the standards, key ones of course are equipment. They go through quite a bit about describing the equipment, a little bit about cone design and dimensional tolerances, and those are the key points that we'll talk about today. There's always a section on calibration, and that's important because it does cover accuracy. And you'll see this term full-scale output, the acronym FSO, and the full-scale output is essentially the capacity of the cone, the maximum capacity for each of the sensors. So we'll come back to this. And procedures, of course there's often detailed procedures in the standards, but some of the key elements are the zero load readings, and we'll talk more about that. Saturation, I won't cover that much today unless it comes up in questions. That's sort of specific to piezo cone, how to saturate the cones. But most of the manufacturers have recommended ways to do it. They're all pretty good. The key is that you may saturate the cone up at the ground surface, but then you have to turn it upside down and start pushing it into the ground, and you may have several meters of unsaturated soil to get to before you get to the water table, and so the issue of loss of saturation. And then if you're pushing through very dense dilated materials, the risk that you actually generate negative pore pressures that may desaturate the porous element. And then there's push rates. The standard rate is 2 centimeters a second, but there is a little bit of flexibility. It doesn't have to be exactly 2 centimeters per second. In general, it's not that sensitive to rate. And then an issue about temperature, which we'll talk about. And then there are corrections, which we'll talk about, and checks and maintenance, which we'll discuss. So key elements about equipment, the cone has a 60-degree apex angle. The original cones were 35.7 millimeters in diameter. That makes a 10 square centimeter cone. But quite a few of the cone standards now allow cones to vary a little bit in size. ASTM allows it to go up to 15 square centimeters, which is almost 44 millimeters in diameter. And the ISO standard actually allows it from as small as 5 square centimeters to as large as 20 square centimeters. But certainly around the world, the 10 and 15 square centimeter tend to dominate practice. Historically the 10, but increasingly the 15 square centimeters is becoming popular. And in some parts, particularly in the offshore world, the smaller 5 square centimeter cones are also becoming quite popular. And there are some even mini ones of 2 square centimeters, but probably out of the minier cones, the 5 is probably a little bit more popular. One of the reasons for the popularity of the 15 square centimeter cone is that typically the push rods are 35.7 or roughly 36 millimeters in diameter, roughly the same size as a 10 square centimeter cone. And so when you're pushing a 10 square centimeter cone, you actually have to have a bump in the rods to push the soil away from the rods to reduce the friction on the push rods. And so that's often referred to as a friction reducer, and it's typically located approximately a meter behind the penetrometer. Sometimes a little bit closer, but ideally something of in the order of a half or a meter behind the cone. So the advantage of the 15 square centimeter cone is if you're using the standard 10 square centimeter push rods, the 15 square centimeter cone is already larger than the push rods and so has already reduced the friction, so there's no need for a friction reducer. And so studies have shown that it's actually easier to push the 15 square centimeter cone into the ground than it is the 10 square centimeter cone, because the 10 square centimeter cone has roughly a meter of 10 square centimeter rods and then a bump, and the bump is nominally about 15 square centimeters in cross-sectional area. So that's one of the reasons for the popularity of 15 square centimeter, is it's actually easier to push it in, so therefore for a given reaction force you can push it a little bit deeper than the 10 square centimeter cone. And also the cones are a little bit bigger, they're more robust, a little bit easier to make and put all the electronics inside. Now the friction sleeve, originally 150 square centimeters for the 10 square centimeter cones and 225 square centimeters for the 15 square centimeter cones. Now there are some 15 square centimeter cones that have 200 square centimeter cones, but most of the standards now specify it has to be 225, and that's based on a length to diameter ratio to ensure proportionality of the geometry, not proportionality of the area. The preferred filter location, the common one is behind the tip, often referred to as the U2 location. Originally when piezo cone were first developed and pore pressures were first measured, it was often measured on the face of the cone, but after some debate in the 80s, there was a general consensus that it was a little bit easier to put it behind the shoulder. And one of those reasons is a little bit easier to saturate there. The filter element is more protected. It tends to get damaged when it's on the face. And the U2 location is the location that you need to measure the water pressure to make the unequal end area corrections, which we'll talk about in a second. And then on equipments, there's also limits on dimensional tolerances. And so although these dimensions are given, then of course cones will wear a little bit, and the manufacturing has some variability, and so they give acceptable tolerances on the dimensions, which we'll talk a little bit about later. Here, this is an illustration of the range of magnitude of the measurements they're going to take. So this is the original soil behavior type of tip resistance on a log scale against friction ratio. Just a reminder that the friction ratio is the sleeve friction divided by the tip in percent. And here, this is a version of the chart where it's dimensionless. So the tip resistance is divided by atmospheric pressure to make it dimensionless. So in megapascals, the 10 would be 1 megapascal, whereas in tons per square foot it would be 10 tons per square foot, because what happens is QC, as we've seen before, can be a very small number, maybe 5 or 6 atmospheres, and because soft fine-grained soils, when the cone is pushed in, it's often undrained, so the pore pressure can be a large number, sometimes 80 to 90% of QC. So if QC is like 5 atmospheres, U2 could be 4 atmospheres, and then you have to make a 20% correction of that. And so it's a fairly significant correction. So ideally, cones should have a high net area ratio up around 0.8 so that the correction is 20% of the water pressure. Now some of the cones and some manufacturers have cones where the net area ratio is down as low as 0.6, and so 1 minus 0.6, of course, is 0.4, so you're making a 40% correction of the water pressure, which is double what it is if it's 0.8. So ideally, you want cones that have a high net area ratio, up around 0.8, so that the correction is a little bit smaller. But the key is, as long as you measure the water pressure, you can make that correction. Of course, if you're not measuring the water pressure, then you can't make that correction, and therefore QC is not as accurate as QT. Now, there's likewise an unequal end area effect on the friction sleeve, because in the early days, when people lowered these cones into water, they noticed that when you're lowering the cone in water, of course, there should be no sleeve friction because the water generates no frictional stresses on the cone. But there is pressure acting on the ends of the sleeve, and if they have unequal end areas, then it produces an unequal force. And so in the example I'm illustrating here, if the area is bigger at the bottom, you get a positive force. Of course, some cones in the early days had areas that were larger at the back, so they had negative forces. And so this is the official correction, which requires these areas at the bottom and at the top and the surface area of the cone. But basically, depending on the size of the cone, obviously it's a little bit better the bigger the cone, so the biggest surface area AS of the sleeve makes the correction a little bit smaller. And obviously the smaller the end areas, the smaller the correction is. And the water pressure at the bottom and at the top is not always equal. There's a little ratio between the two. It's depending on the type of soil, it's somewhere between 0.5 and 0.8, the variation between the top and the bottom pore pressure. So in very soft clays, this can be a fairly significant correction. Most people don't make the correction because typically we're not measuring the water pressure at both locations, U2 and U3. Often we're only measuring it at 1. Now you can make an assumption of what the ratio between the two are and make the correction, or it's usually a little bit better if you're using a cone that has equal end areas, so the areas at the end are equal, and so if there's equal water pressure then there is no correction, but with unequal water pressure there is a small correction. So as long as they're equal and if the areas are very small, then the correction is very small. So it's better to have small equal end area sleeves, and in fact some standards ASTM actually requires cones to have equal end area friction sleeves to minimize this unequal end area effect. So to give you an example of how big the correction could be, Tom Lund back in 2006 published a little study at NGI where he looked at different cone designs and gave their dimensions. Admittedly this was back in the early 2000s. So some of these manufacturers have changed their dimensions a little bit, but so these are just for illustrative purposes. And you see quite a few of the cones do not have equal end area. The Vandenberg one and the Gregg at that time did. And so, here's I've given an example for a typical soft clay where you might have a pore pressure of 300 kPa at the bottom of the sleeve and then 210 at the top. Those are sort of typical ratios, typical excess pore pressure values. And the sleeve friction, if it's a soft clay, may be around 10 kPa. And so you can see that with some of them, in one in particular, you can see it's a significant error in a very soft clay. So obviously it's much better to have cones that have equal end area sleeves and ideally small areas so that the correction is, or the error is very small because very few people actually make the correction. Now obviously when you get into stiffer soils where the sleeve friction might be 100 kPa, and of course the pore pressures could be a lot smaller, and so of course these errors of course become a lot smaller in stiffer, particularly coarse grain materials. So it's only in soft fine grain materials this becomes an issue. So when we talk about calibration, here's a sort of a classic example of a calibration. This was a diagram Professor Campanello and I published many years ago. It appears in some of the standards. And so you've got load on the horizontal axis and then output from the sensor on the vertical axis. And of course you get a calibration line. Now of course it's exaggerated here to show the various errors, the repeatability, the nonlinearity, and the hysteresis, etc. But of course most modern cones, they're strain gauge load cells, they're temperature compensated, and they often have excellent repeatability with very little nonlinearity and hysteresis. So basically you get this beautiful, pretty well close to a straight line with very little nonlinearity error. But the big issue is this zero load drift, is that when you load the cone up and bring it back to zero load again, the output may not come to exactly zero output. And so there's a small drift in the strain gauge output, which for very soft soils where you're measuring way down at the bottom here, that zero drift becomes significant. And the full-scale output, it's common to have a high-capacity cone, so it's not unusual for the tip full-scale capacity to be 100 megapascals, which is 1,000 tons per square foot, which for a 10 square centimeter cone is nominally about 10 tons. So often they're referred to as 10-ton cones. The difficulty referring to it as a load is that they're load cells designed to measure stress, and so it is a function of the size of the cone. So for a 15 square centimeter cone designed to go to 100 megapascals, it's a 15-ton cone, whereas for the same full-scale output, a 10 square centimeter cone is a 10-ton cone. So I prefer not to quote in sort of 10 or 15 or even 20-ton cones. It's better to give them full-scale output in terms of their stress. And so load cell design, you can have load cells designed that have separate load cells that measure the tip and friction separately with two separate load cells. These tend to have better accuracy for sleeve frictions because each load cell will have a separate zero load drift, but you're measuring the load separately, so you can correct each load cell independently. But in the 80s, in Europe in particular, it became quite popular to use subtraction design load cells. And these are load cells that have two loads in tandem here. And so the tip is measured on the first load cell, and then the tip plus the friction gets added on the second load cell. So of course, to get the friction load, you actually have to subtract those two loads, hence they're referred to as subtraction cones. These tend to be a little bit more robust because the load cells tend to be a little bit thicker and therefore more robust. But they're not so accurate in measuring sleeve friction because you have to subtract these two quite large loads to get the small load of the friction sleeve, and so they lose that accuracy. Plus, of course, each of the load cells could have slightly different zero load drifts, and so it gets a little bit more complex to manage the zero load drift effect on subtraction cones. So in general, subtraction cones don't have the same accuracy on sleeve friction that the separate load cells do. So a number of the standards now are beginning to specify application classes, and typically there's 3 of them. It depends on the standards. Some have 4, but typically you see 3. So here the International Reference Test Procedure gave 3 classes. Class 1, the very highest class of accuracy, you can see said you had to have accuracy of about 50 kPa on the tip, 10 on the sleeve, and 5 on the pore pressure. And then those numbers get bigger as you go to class 2 and even larger on class 3. So in general, class 1 was designed for very soft soils, and then 2 would be for mixed soils, and then 3 would be basically limited primarily to the denser and stiffer soils. And the more recent ISO has similar ones, except they've tightened it up a little bit more. The numbers have got even smaller for class 1. So class 1 in the new ISO is actually a very tough standard to maintain. These are very small numbers. So either you have to have a very low capacity cone with excellent zero load stability to meet these numbers. And for application class 1, they recommend that it must be CPTU, so you measure tip, sleeve, and pore pressure. And that's primarily because you need that pore pressure to make the corrections to the tip resistance. And for class 2, it can either be just regular CPT, just tip and sleeve, or you could use CPTU that measures tip, sleeve, and pore pressure. And then, of course, class 3 can be either one, too. So here's a summary. Application class 1 is generally limited to soft to very soft soils, not for mixed soils, because if you hit some dense layers, you may damage the cone. And tests should only be done with CPTU. So class 1 is typically only where you have very soft soils near the surface and you're not going to encounter any denser layers, which is not that common an occurrence. Application 2, which is the more common one, is mixed soil conditions, where you may go from soft to dense layers, and you can use the results for profiling, material identification, and engineering properties, although there may be some limits and restrictions on the very soft layers. So you may not have the same level of accuracy in the very soft layers if you've got a higher capacity cone to get through the dense layer. And then class 3 is primarily denser soils, and you can use it for all things, profiling, identification, and engineering properties, because the materials are primarily dense or stiff. So let's talk a little bit about accuracy. Most strain gauge load cells have an accuracy of about 0.1% to 0.5% of full-scale outputs. Most of them are actually pretty close to 0.1%. So a well-designed, manufactured, and well-maintained strain gauge load cell can have 0.1% of full-scale accuracy. So basically, the full-scale output divided by about 1,000. So if you had a relatively large capacity cone that had a full-scale output capacity on the tip of 100 megapascals, that's 1,000 tons per square foot, then of course that means you have an accuracy of about 0.1 megapascals or 1 TSF. Now of course it's between 0.1 and 0.5, so it could be as large as 0.5 megapascals or 5 tons per square foot. So if you're pushing in dense sands or stiff clays where the tip resistance is in excess of 10 megapascals or in excess of 100 TSF, then you're going to have excellent accuracy. So if you've got an accuracy of about 1 to 5 TSF in 100 TSF or more, then of course you're going to have an accuracy of about 1 to 5%. So usually an accuracy of better than 1% in these dense soils. Whereas in soft clays, of course, the tip resistance could be much smaller, less than 10 TSF, and you're going to have less accuracy. So if you've got an accuracy of 1 TSF and you're measuring less than 10, then you have an accuracy of sort of less than 10%. Now remember, this is a lot better than it used to be with the older tests like the standard penetration test, but clearly not as accurate as you may wish it to be. And so if you've got very soft soils, you really need a lower capacity cone. So rather than have a 100 megapascal or 1,000 TSF capacity cone, and remember for a 10 square centimeter cone, that was nominally a 10-ton cone. So you may choose to go to a 5-ton capacity cone, which would give you twice the accuracy. So things would get better with a low capacity cone. So often what happens is if you're not 100% sure about the site, then typically you use a high capacity cone first, punch a few holes, verify, yes, that you have soft sediments and that you would like improved accuracy and that you don't have any dense layers that you have to get through near the surface, and so you could then use a lower capacity cone to improve the accuracy and then to check it against the higher capacity cones. So the key factor is zero load drift. That's going to be the biggest factor that controls the accuracy, and the key is that the zero load drift must not exceed the accuracy, so ideally very small for soft soils. So in general, the tip resistance is more accurate than repeatable than the sleeve friction. To get better accuracy on the sleeve, I prefer that you have separate load cells to improve the accuracy of the sleeve, and you also want equal end area sleeves to minimize the water effects on the sleeve. And ideally, the equal end area sleeve should have a small end area to get even better accuracy. And check the tolerances on the sleeve. Most standards allow that the sleeve should never be smaller than the tip, but they can be slightly larger. And a lot of the standards specify that they can be up to 0.35 of a millimeter. Now, that's not very much, but it's a noticeable increase. So it's noticed to be a little bit larger than the tip. And I'll comment about this a little bit later. My preference is that sleeves should have the same diameter as the tip, because if it's slightly oversized, and some manufacturers do make their sleeves slightly oversized, still within the tolerance, but slightly oversized. The downside with that is that with wear, they will wear, and so they may start off being slightly oversized, but after a few soundings they begin to become equal to the tip, and so there's some variability even though they're within the tolerance of the standard. And so tip is more accurate than the sleeve, and tip is usually more accurate than pore pressure, except of course in very soft fine-grained soils. And so if you've got soft fine-grained soils where the water table is close to the ground surface, so you get large excess pore pressures. So the tip resistance can be very small, but the excess pore pressures can be very large. So in that particular case, the pore pressures can actually be more accurate than the tip resistance. But in general, the tip is more accurate and more repeatable than pore pressure. pressure. And that's because of potential loss of saturation in stiff dilative soils where the pore pressures can go negative and cause temporary loss of saturation and therefore loss of accuracy. And here's an example. This is in a way somewhat similar to that example I showed before. It's from San Francisco. It's 60 meters deep. Again, you've got this sort of 4 meters of a stiff, often fill to get through, then essentially normally to lightly over-consolidated clay, locally referred to as young bay mud, and then sort of a sandier zone, and then into old bay muds, and again, sandier zone. And you can see in this particular example, 2 CPTs done quite close together, just within about a meter of each other. Excellent repeatability on the tip, and excellent repeatability on the sleeve. Friction ratio is almost identical, and pretty good repeatability on the pore pressure. But you can just see that the red location, which is location 26, was pretty good. The pore pressure responded quite well when it started going into the soft clay. But at location 27, saturation wasn't quite so good, so a little bit sluggish for a couple of meters, but then started to respond quite well. And then when it went through the sandy region around 24 to 26 meters, the location 27, the green one, slightly negative, and so caused air bubbles to come out of solution again, and then again a slightly more sluggish response going back into the clay. And so that's one of the challenges of pore pressure, is that it may start off initially saturated, but you could in fact lose saturation, but then gain it and then lose it again, gain it and lose it again. So interpretation of pore pressure data in mixed soil conditions can be quite complex. So why is the pore pressure data so complex and often lack repeatability? And really it's the complex stress and strain field around the cone, and that in strongly dilative soils you can actually get negative pore pressures at the U2 location. And the reason for that is that on the face of the cone you often get very high pore pressures because it's a region of high compression, high octahedral stresses. Of course, a lot of shear stresses too, but you've got both of them together. Whereas when the soil comes around that shoulder, there's a large stress relief in terms of normal stresses, but large shear stresses. And so the pore pressure response is dominated by the shear response. So if you have a dilative soil, you can get negative pore pressures. But pore pressures can be very good in soft, fine-grained soils with a high groundwater table. And that's because you've got high positive pore pressures throughout and a short depth often to the saturated soils. So Campanella and I, back in the early 80s, published this little diagram, which is still quite nice. It's a plot of basically the normalized pore pressure, normalized by the hydrostatic equilibrium water pressure against the location behind the cone. And so right at the bottom here is right on the tip, and then the U1 is halfway up the face, U2 is just behind the tip, and then U3 is up behind the sleeve. And you can see that in normally consolidated clays, you get quite large pore pressures, maybe 3 to 4 times hydrostatic, and then behind the sleeve it drops just a little bit. You still get pretty large pore pressures. And in over-consolidated clays, the tip resistance becomes much larger, so the pore pressure on the face gets bigger. It can be 10, 15, 20 times hydrostatic, so you can get very large pore pressures on the face of the cone. But then these stiffer soils are more dilative, and so you can get very low pore pressures and sometimes even negative pore pressures in very stiff over-consolidated clays. Or in some clays, if they're cemented and slightly sensitive, then you can still get large pore pressures behind the tips. You can see it's a complex stress regime which makes both the measurement and interpretation of the pore pressure in mixed soil conditions quite complicated, which is why I'd stated that in general the tip resistance is still the most dominant parameter that's used for a lot of interpretation, because it is a little bit more accurate and repeatable in general, other than in very soft, uniform soft clays. So why is the sleeve friction often considered unreliable? And that's partly because data in soft clays, when they compare cones, often they're comparing cones where some cones have separate load cells, some cones have subtraction, so you see variability in accuracy and repeatability, and some cones have unequal end area, which introduces large errors. So obviously for improved accuracy, experience has shown that if you have cones that have separate load cells, equal end area sleeves, especially with small areas, and you check the dimensional tolerances, in other words, you avoid oversized sleeves, then you can get very repeatable sleeve friction measurements as well. Now, why is this important is sleeve friction is not used a great deal in interpretation. Its most common applications is for soil classification purposes, and I've often commented before that even in those situations it's not highly sensitive to accuracy of sleeve friction because those charts are on a log scale of friction ratio, so they're somewhat forgiving, particularly for soft clays. The zone of clay on those charts is very large, and so they're very forgiving. But if you do want to use it to estimate the remolded strength of the clay, then it is important that you get very repeatable measurements. And when you follow these rules of separate load cells, equal end area sleeves, and avoiding oversized sleeves, then experience has shown that the sleeve friction is in fact very close to the remolded strength of the clay and is quite repeatable. And here's an example. This is from a soft clay site. This is actually from the University of Berkeley research site at the Hamilton Air Force Base in San Francisco Bay Area on the north side of the bay, essentially normally consolidated young bay mud with a little bit of a crust. And you can see excellent repeatability with two soundings here. You can see the tip resistance is repeatable within 20 kPa, so that would put it in a class 1 on all the standards. Sleeve friction, you see, although it doesn't look quite as repeatable, it is within 2 kPa, so the scale has been blown up here, from 0 to 50 kPa, so this is a blown up scale, but it is within a couple of kPa repeatability. And the pore pressure, again, you're going out to almost 600 kPa down to 20 meters, and so there is a little bit of variability, within 20 kPa, and actually that would be just outside the class 1. So although this is an excellent set of data, tip and friction are within class 1, but the pore pressure would be slightly outside of the class 1 designation. So you can see the challenge to get pore pressure within class 1 designation, even at a carefully controlled site where the water table is very shallow and it's essentially a normally consolidated clay. So it's quite difficult. So oversized sleeves can produce more variability, and to illustrate that, here is that same site, and two cones, both happen to be low capacity cones, but the light green sounding was where a slightly oversized sleeve was put onto the same cone. So you can see excellent repeatability on the tip and pore pressure, but now the sleeve has changed by about 4 or 5 kPa. Now that's not a very big number, but we're only measuring sleeve frictions of 5 kPa, so it's almost 100% error in the measurement by using an oversized sleeve. And what we also found is that when we did a third sounding with that same oversized sleeve that had now been used once, the measured sleeve friction dropped down a little bit and was getting closer to the one that was of equal dimension. So obviously it was already beginning to show signs of wear. And so oversized sleeves are not recommended because they do introduce added uncertainty to the accuracy of sleeve friction, and added uncertainty due to the wear of the sleeve friction. So I don't recommend it. Now in stiff soils it's not a problem. Dense sands, etc., not a problem. It just becomes a problem in the very softer soils, either very loose sands or very soft clays. So a checklist primarily for contractors around equipment and procedures. So the recommended one, this is in the CPT book as well as in the CPT guide. I've updated it a little bit. So check the verticality of the thrust machine at the start of every test. Make sure you're going to push the probe in vertical. Check the push rods, make sure they're reasonably straight both at the start of the project and at the start of the test. Check the depth sensor and the rate of penetration at the start of every project and every 6 months. And a good thing to do, a good practice is for depth is to also do a rod count. So let's say you're going to push 50 meters. Just get the operator to count the rods. And so if you push exactly 50 meters on the depth sensor, just double check that you pushed exactly 50 meters of rods, that you didn't accumulate or lose any depth through either inaccuracy of the sensor or the sensor missing a few readings, etc. Check the wear at both the start and the end of every test. So basically, before every test, check for wear on the cone and check that it still is within tolerances. Likewise, check the gaps and seals. Basically, clean the cone after every sounding so that it's clean prior to the next sounding, which means you've cleaned out all the gaps and seals, got rid of any dirt. And of course, the zero load readings, take them at the beginning, at the end of every sounding, and I'll talk a little bit more about that in a second. Saturate and change the porous filter at the start of every sounding. That's the preferred way. Certainly saturate it at the beginning of every sounding, and ideally if you're using relatively inexpensive porous plastic filters, replace the filter for every sounding. Calibration, typically the guideline is, check the calibration every 6 months, although the little footnote here is really it's based on the zero load stability. If the cone is working well and the zero load readings are very stable and they're basically the same as when the cone was originally calibrated, then there's no need to recalibrate it. But of course, if you've hit something hard and the zero load readings shift a little bit, then you need to recalibrate, recheck the calibration of the cone. So it may be more frequently than 6 months, depends how much you've used it and if you've hit anything hard. And of course, check the computer and cables at the start of every project. So zero load readings. Ideally, take 3 zero load readings with the cone in the vertical position. One, of course, before the test, where usually the cone is cleaned and it's just about to go into the ground, so it's just above the ground surface, and you take a zero load reading. And then when you finish the test, as soon as the cone comes out of the ground, take another zero load set of readings. And of course, the cone's dirty, there's soil stuck in the seals, etc. But take that reading, and then dismantle the cone, and of course clean the cone out, ready for the next sounding, and then take another set of zero load readings. This third one is often essentially a repeat of one. If you're continually doing CPTs, then you're going to use the cone again, and so you take another zero load reading at the beginning of the next test, which in a way covers that third reading. So the zero load drift immediately before and after the test, in other words between readings 1 and 2, this is used for interpretation of the test results. That's the zero load drift, and it captures the impact of the test on the data. So any soil that's got in there, you're going to capture that influence by those 2 readings. And then the difference between readings 1 and 3 is the zero load stability, essentially tracking the long-term stability of the cone. And so it's a measure of the correct functioning of the cone. So that's what you want to keep a track of. Ideally, the operator should keep a track of these, and so it's a way of the operator monitoring that the equipment is functioning well, that the zero load stability, the zero load reading is maintaining a stable values and close to the original calibration values that shows that the equipments are operating just fine, and the strain gauge low cells have not got damaged. Most common causes of zero load drift, often still temperature. So although cones are temperature compensated, sometimes there can be large temperature changes. So for example, if it's a hot day, like maybe 25 degrees Celsius, but the groundwater is relatively cool, less than 10 degrees Celsius, then as soon as you hit the groundwater table, there's a fairly rapid temperature change where the cone cools down quickly, and so that creates a sort of a temporary zero load drift that's important to try and correct for. Likewise, if you're pushing through very dense sand and the cone gets warm, and then of course you penetrate into very soft clay, and there's again a bit of a temperature shift there. Ways to overcome this, ensure that you've powered up the cone before you start the test, before you take the initial zero load readings, and also try and keep the cone at a temperature similar to the ground and groundwater. So if you're in an environment where the groundwater is quite cool, then sometimes keeping the cone in a bucket of water helps keep the temperature closer to the ground. And so when you take the zero load reading, the cone is already close to that correct temperature. So for consultants, specify the required standard. So if you're specifying CPT, specify which standard you want the operator to work under, and of course check for compliance. So make sure your field personnel are aware of the standards and they know what to look for. And And then, if possible, specify an application class. Now, you may not want to follow exactly the ones that are recommended in some of the standards, but depending on the project, you may sort of set the application class that you would like for your design purposes. And then supervise and ask for the field checklist. So the supervisor in the field just might want to ask the contractor and say, can I see your checklist that you have, in fact, checked all these things, and let me see you do it. So educate the field supervisors on these sorts of things. So one way to educate your field supervisor is get them to watch the recording of this webinar. Hopefully, if it worked, okay, let's like cut it off a third of the way through. And then, of course, evaluate the results in the field if possible. And I strongly encourage that on bigger projects, whoever is put out in the field to supervise the work, they should have a laptop and they should have software like CPT on their laptop. And because it's all digital data, they should be starting to look at the data and starting to do some preliminary interpretations in the field to get an idea of where the critical layers are, where they might want to take sampling, where they might want to do additional testing, etc. And of course, check the zero-load drift and the zero-load stability, particularly if you're testing in soft soils. So the type of checklist that you want to give the contractor is the type of questions you want to ask them is what type of cone are they using, what type, subtraction, separate load cells, the manufacturer, the size, the full-scale output, in other words, the capacity, and the rated accuracy. What did the manufacturer rate the accuracy of the cone, what standard you would like them to follow or that they follow, the location and size of the pore pressure, if they're measuring pore pressures, is it in the U2 and how thick is it? On average, they're typically around 5 millimeters, but actually get them to document the thickness, get them to document what the area ratio is and how they determined it. Ideally, they determine it by calibration and not just the physical dimensions of the load cells. Whether or not the sleeves have equal end area and maybe what the actual dimension of the end areas are, so you can get a sense of what the potential error might be. And also whether or not they're correcting the data from QC to QT. And ideally, they should present both of you. They should show you the measured QC and then their corrected value. And of course, they should present the zero load readings before and after, and they should keep a record of them. And so you should be able to ask for that record at any time. Also, the depth interval that the data is being recorded, you'll often see that in the data file, but you just confirm what depth interval they use. And then if you are measuring pore pressure, if you're doing dissipation tests, do they clamp the rods or not? Ideally, you want the rods clamped. You don't want unloading of the rods, and you certainly don't want any movement of the rods during the dissipation test. And then if they have an operational checklist, confirm and get a record of it. And if there's any pre-drilling or hand augering or drilling out in the hole, any procedural activities, confirm what they are and record them. So quality control, how do I evaluate the data I've got? So let's say I wasn't involved in specifying it, but I've been given data. How do I evaluate it? And I mentioned about the software CPT. You can get it from the website Geologismickey, and I was hoping that we'd have time that I might show you some examples on it, but I think we'll stick to the slides because we might be running out of time. And so what do you do with what you have? So if someone presents you with the data, what do I do if the data is not ideal, that maybe there has been some zero drift, and how do I identify that? So illustrate with some examples. So what do you check for? Check for data spikes, sometimes rod breaks. In the old days, they were quite common. Now less so. Data acquisition systems have got a lot better. In the old days, it was quite common that every time you paused to add another rod, that little spike would show up in the data, and ideally you'd like to remove it. But you can get data spikes for other reasons, and I'll illustrate some examples of that. And then sometimes if there has been a relatively large zero load drift because you're pushing in very soft soils, sometimes you get zero or negative readings on the tip or sleeve. It's often more common on the sleeve. What do you do about that rather than just discard the data, can you make a correction for it and continue to make use of the data. And I'm a big proponent of making overlays, so again using the software in the field, checking for consistency, that when you overlay the data that the data is reasonably consistent. Check for loss of saturation and pore pressure, and ideally carry out some dissipation tests, often at the end of the sounding, the deeper part of the sounding, so that you can get a reasonable estimation of the piezometric level. A lot of people do CPT with pore pressure measurements, but don't do dissipation tests. And even if it's just one, just do one at the end of the sounding or at some convenient location during the sounding. So if you're pushing through mixed soil conditions and you're pushing through clays and sands, then sometimes stop within the sand layer and do a quick dissipation test just to verify the piezometric level and the piezometric conditions. So determine where the groundwater level is and determine if it's hydrostatic or not. So here's some examples. So the one on the left is a data spike. So relatively basic data here, but you see that there's a single data spike at 4 meters, and if you go into the fire, you see it's a single value. And of course, it's rare that you'll get suddenly a 3 or 4-fold increase in tip resistance in a single reading. It's possible, but very unlikely. I mean, because if you hit a dense layer, you get several readings, not just a single reading. And in this particular example, there was really no effect on the sleeve friction, no effect on the pore pressure. It was just a single reading on the tip. And it could have been electrical noise or a depth triggering issue. But in this particular case, with the high one, it was an electrical spike in the data. And so the ability to remove that, and you see what happens when you remove it. It looks a lot better. It's relatively simple to do that. This is more common examples. So here's some data spikes. They're not rod breaks. They're just spikes down of data in this material. I'm not quite sure exactly what caused it, but you can see that they're data spikes. And from the pore pressure, you can see there's no evidence that these are layers, because they are single data points. If they were thin layers, often it would be several data points, and you would see it in the other channels. So you can correct for that. And then here's some data spikes. This is in a soft clay. These are predominantly rod breaks. They're predominantly every meter in this lower section. And here, this is a soft, normally consolidated clay for 20 meters. You can see increasing tip resistance, essentially increasing sleeve friction. Although you can see in the upper 3 to 4 meters, the sleeve friction actually went negative. And this may be a case of zero load drift, possibly due to temperature changes. And you can see that in that shallow depth, the sleeve friction would have only been a few kPa. So it's very easy to be out by a couple of kPa, which means the numbers could go 0 or negative. And so you just need to sort of bump them over. And so in this particular example, where it's just been bumped over by adding 1 or 2 kPa in that section, to sort of correct the data and removing these spikes. Now, of course, when you do that, some people say, "Wow, how can you do that? You sort of added that number. Wouldn't that haven't you really made a major change to the data?" And the answer is, well, not really. If you go to the interpretation, this is what happened when you interpreted the raw data. So first of all, you got these data spikes down here, and then there's missing data. And the reason it's missing data is because the software typically can't interpret the soil type here, because if the sleeve friction goes negative, then the friction ratio goes negative, and the software is unable to compute a soil behavior type. So the software is unable to determine, well, is this clay? Should I determine an undrained strength and an OCR? And so you get a gap in the data. Whereas when you shift the sleeve friction just slightly over into the positive region, it doesn't change fundamentally the interpretation, but it just fills in the gap and allows the computer to fill in the missing data. And of course, although you can't see it that well, the spikes have been removed below. And so here's the software CPT. So I'll just get to the summary slide, and then I'll open the software just to quickly show you some of those examples. So in most cases, CPT data is reliable and representative of the ground conditions, certainly much more reliable than the standard penetration test. You can reduce the chances of poor quality data by making sound specification of the standards, clearly specifying which standard you want to follow and make sure that it is followed, and then evaluate the data in the field. So train your field staff who are supervising the work to know what to look for, and then good data processing software so that you have a way of processing it. So what I'm going to do is very quickly see if I can open the software to illustrate some examples. And now, as we found out before, is that my computer tends to freeze when I shut down the PowerPoint, and that's exactly what's done. So let's take some questions while my computer tries to warm back up again. So a couple of questions. One was a comment on using dummy cones. And I think the reference here is some of the literature will refer to the use of dummy cones. And what that means is that, let's say you have a site that's predominantly soft clay and you want to use a low capacity cone to have increased accuracy, but there is a bit of a crust, maybe a fill, a meter or so of maybe quite dense fill, compacted fill that you need to get through, or a gravel layer that's going to be quite hard to push through. And you don't want to push the sort of low capacity cone through this gravel layer to get into the soft clay. And so what some contractors will do is just basically use what's referred to as a dummy cone, but it's a cone rod with a conical point on it where there's no cone there, and they just use that to punch a hole through the dense layer, the surface layer, and then pull it back out again, and then take the regular cone and then go through the pre-punched hole. And what you need to do is make sure that you eventually correct for the fact that the data in that pre-pushed area doesn't represent the real soil conditions because you pre-pushed it. Next question, how to estimate pore pressure values measured during CPTU performance to check validity of the measured values. Now that's basically they're saying, so if I've measured pore pressure, how do I know if they're right? Well, there's a couple of things. One, of course, if you do a dissipation test and the pore pressures dissipate to equilibrium and the equilibrium's consistent with what you think the groundwater conditions is. In other words, if you think the water table is at a certain depth and you think it's roughly hydrostatic, let's say the water table is roughly at the ground surface, so at 10 meters, hydrostatic water pressure would be 100 kPa approximately. And so if you did a dissipation test at that depth and it comes pretty well to exactly 100 kPa, then you know the pore pressure sensor is working just fine and there's no reason to question the values. If you actually want to try and sort of calculate a predicted value, now that's a bit tough. Like in soft clays, you'd have to estimate what the undrained strength of the clay is and then calculate what the excess pore pressure could be. And you can do that. So you could take the measured tip resistance, estimate the undrained strength, and then use that to estimate the pore pressure and see if that's roughly the value you got. Not many people do that because in a way you often work backwards. Is you could estimate the undrained strength from the tip and then take the measured pore pressure and estimate the undrained strength from the pore pressure and compare it with the tip, and if they're close, then you know that all the measurements were fine. So is this statement true? The measured pore pressure values in an unsaturated layer are not reliable. Like so many statements, it depends. If you have an unsaturated layer, so first of all, what do you mean by unsaturated? So, you've got the piezometric level where the water pressure is zero. Nominally, we often refer to it as the groundwater level. So that's where the water pressure is zero. But above that, the ground could be saturated. Depending on how fine-grained the soil is, you get a capillary zone, so you get saturated soil above that. And so in that saturated zone, the equilibrium water pressure would be negative, negative by the height above the phreatic surface. And then above that, the soil becomes unsaturated. Now, initially, it could be unsaturated where you've got air bubbles, so relatively high level of saturation, but air bubbles. And then further above that, you've just got really small elements of water when mostly air in there. And so when you have a typical porous element that uses a diaphragm to measure the pore pressure sensor, those diaphragms can go on the negative side, but they can only go negative up to 1 atmosphere, and then the sensor itself desaturates. So if it's unsaturated and the negative pore pressures are only slightly negative at 0, then it is possible to measure reasonably accurate negative pore pressures in unsaturated soils, as long as the negative water pressures are not very negative. In other words, they must not exceed -1 atmosphere. Now, of course, if you have an unsaturated fine-grained soil like clay or silted clay, the negative pore pressures can be very highly negative. They can be several hundred atmospheres negative. And so it's clearly impossible that the type of pore pressure sensor on a cone could get anywhere close to measuring those sorts of negative pressures. So the statement, not strictly correct, but in some cases you could be pretty close. Next question, where is a copy of the International Reference Test Procedure? Is there one proposed for seismic cone? Okay. The International Reference Test Procedure, you may be aware, I think I've mentioned it in previous webinars, that we're organizing another CPT conference. We had CPT 10 in 2010 here in Huntington Beach in California. The next one is in 2014, it's next May, so CPT 14. And if you go to the website, which is www.cpt14.com, we have a library there, and we are posting quite a lot of material on there. You can access all of the CPT 10 technical papers. You can access papers from CPT 95 as well as from ESOP 1, which was back in 1974. So with the assistance of the Swedish Geotechnical Institute, we've put a lot of these old publications on there. And I'll also make sure that a copy of the International Reference Test Procedure is also available there for free download. Is there a standard distance, a minimum distance to any friction reducer behind the cone? I had sort of said typically it's roughly 1 meter behind the cone, and often it's there because it's put sort of halfway up the first rod, so it's normally about 1 meter behind the tip. Usually in terms of how far away it should be, it typically has to be 10 diameters away from the diameter of the friction reducer. So let's say the friction reducer is 15 square centimeters. So that's about 44 millimeters. So ideally about 10 diameters away from that. So that would be about 400 millimeters, so about half a meter. So dimensionally, normally the minimum distance would be about half a meter, but it depends on the size of the friction reducer. But you can see the advantage of a 15 square centimeter cone is you don't need to use a friction reducer. So in which cases can mechanical cones, Begemann type, be accurate and reliable? Basically, when we talked about those 3 classes, class 3 was designed for stiff soils. The Begemann cone is often just fine for the denser soils because the readings are much bigger. But you do have to keep in mind that the Begemann mechanical cone has a different geometry to it, and particularly for the sleeve. So the sleeve is always a little bit different than the electric cone. But in general, for stiffer soils, the mechanical cone is not that much different from the electric cone. When you get into very soft soils, there can be bigger differences simply because lack of accuracy on the mechanical cone and the sleeve friction itself, the geometry is quite different, and so the sleeve friction on the mechanical cone can be quite a bit larger than the electric cone. So you have to be a little bit cautious. And certainly there's a tendency towards using high-quality electric cones in soft sediments. So if the cone is used in the low range of the load cell, does that have implications on calibrations? Well, when I talked about low-capacity cones, so these are cones that have a lower full-scale output. So their full-scale output is smaller. But it's also possible that you can take a high-capacity cone and sort of recalibrate it over the low range. And that's based on the observation that there is a little bit of hysteresis in the, a little bit of non-linearity in the calibration, and therefore, by doing a calibration over a lower range, you get slightly better accuracy. And so some contractors do in fact do that, and it's becoming a little bit more common in the offshore industry, where they'll take a higher capacity cone and they'll just calibrate it over the low end. And that's actually quite a good idea, because nonlinearity is not a big issue. And so if you calibrate it over, say, like the lower half, you get better accuracy over the lower half. And if you do in fact push into the high end of the capacity, you still have pretty good accuracy, because of course now you're measuring really large numbers. And so although the percent error gets a little larger, the numbers are much larger, so it's more forgiving. How often should an operator calibrate the cone or load cell? And as I commented during the talk, is although we normally say every 6 months, the reality is base it on the zero load stability, because of course you may have a cone that's not been used very much, and so of course it's almost brand new, and so there's no need to have it recalibrated if it's essentially brand new, because it hasn't been used very much. But if it's used a lot, then you just track the zero load stability readings, and if those zero load stability readings are very stable, there's no need to recalibrate it. However, if they begin to drift, or if you say hit a boulder and there's a sudden shift in the zero load stability, then you do need to take the cone out of commission and have a check calibration done to make sure the calibration is still valid. Because experience has shown that although the zero load may have shifted, quite often the slope of the calibration stays the same, it's got shifted by a zero load shift. And so just because the zero load has moved doesn't necessarily mean that the calibration is no longer right. You just need to just check that it's still the same calibration that you had before, and if it's not, what's the new calibration? Does or will ASTM standard include application classes? I have no idea. I'm not involved in ASTM standards, so I don't know, but I suspect it'll evolve and begin to define some application classes, since the other standards do, and there tends to be uniformity between the standards. So yes, there's a strong likelihood that that will happen. How do we deal with negative values in soft soils? Well, hopefully I talked about that. I showed the example, and unfortunately my computer truly has frozen. And so it's not cooperating with me to open the software. Oh, it might do now. There we go. Okay, we'll open it now. And so I said, often the negative values are on the sleeve, and so you can just add a little bit to do that. So let's illustrate that now. Really not having a good day with my computer, having shut down the webinar halfway through, and now my computer's freezing. I tried to illustrate it here. I'm obviously just going to go back. Here there was negative sleeve frictions, and so what I did is I went into the software. The software has a CPT data element that allows you to either add a little bit to the sleeve friction, or to switch negative or zero values to a slight positive value. And that's what I did here. Is I said, okay, there's a little routine that will search the file for either zero or negative values, and then convert those to a small positive value, which is what I did. Let's see if it's working. Here we go. So let me open up the example. So here's the one with negative values. So there are a number of soundings. I'll show you an example. So here's that one I showed you in the slide. So soft clay. So here's the profile, predominantly soft clay, and you can see that the raw data went negative. And so if I actually show you on the values here, I can go in and actually look at the values at this depth, and you can see that it went slightly negative here, negative 0.1 or 0.2 kPa. So just a tiny amount, but it did go a little bit negative. So there is a feature in the software under CPT data. There's a filter feature, and one of them is negative values. And so you can select sleeve friction and say, okay, I want to apply it to also zero. So what it does is searches for either zero or negative values, and you replace it, and you can say, okay, replace it with 1 kPa. since this is in metric, so it's in KPA, and I say yes, do that, and it's saying, are you sure you want to do this? And say yes, and boom, you see it's just added a little bit there. And so what's happened now is now the friction ratio got finished, the soil behavior type got finished, and so the data was sort of off the chart and now just got shoved into the chart a little bit. So let's see if I can. So you can see here's another example. So here's another example with some negative numbers. And so if I zoom in on this section, just look at that section and go to the chart, you can see it's off the chart. It's not showing up. Whereas if I just add a little bit to it, let's go back to the raw data. So here's it corrected. So a few KPA added. So if I go to the chart, you can see now it's been added, just pushed it sideways over to push it back onto the chart. And so when you go to the estimated parameters, here's the example. So here's undrained strength ratio, and OCR. So this is the example. Here's the other one that I was looking at. So it just fills it in. The undrained strength ratio is fine. So it's a way of sort of coping with less than perfect data, but still being able to extract the maximum amount of information out of it that you can. Obviously, this one's not too bad, just a little bit, and you can add it a little bit. 3 had a little bit more. There was a longer section. But what's quite nice is that if I look at the overlay plot, so I'm looking at the overlay of the raw data, here's the overlay, and you can see that the tip resistance is pretty good, pore pressure is pretty good, so it's clearly showing it's a consistent site, and the friction ratio, 2 of them were quite good. Here's the one that I've just corrected, and the other one, this was the one that's got the negative values. You can see the friction ratio is clearly off here. So you can see, and I can switch this to measured sleeve friction. It's a new feature of CPT that when you're in the overlay plot, you can either look at measured friction or friction ratio. You can switch between the two. So you can see that by adding a small bit here, you can see that ideally I should have put a linearly increasing value from nominally about 1 up to down to around 5, down at 10 meters. That's probably the correct value, but by adding just a little bit, I'm still being conservative, but at least it gets the software to work, and you can start getting estimated parameters. And here's the interpreted parameters. So I know it sounds like you're fudging the data a little bit, but you're not. You're just taking data you've got and allowing you to run computer analysis on it. Now see these spikes here, these little rod breaks. You have a feature to get rid of them. So again, under filters, there's a spike filter. So you can select which channel you want. I'm going to deselect the pore pressure one, and I'm just going to filter the tip and pore pressure to get rid of these spikes. And if I just move the slider over, it gets rid of the spikes a little bit. And if I say, okay, accept that, and now you'll see those spikes disappear. See the spikes disappeared. So now when I go to the interpretation, it looks a little bit cleaner. I don't have quite so many spikes, and I get a cleaner profile for the interpretation. So it just makes it a little bit better. We're going to have to close. I apologize again that I did inadvertently shut the webinar down. So we lost about 5 or 10 minutes there. I apologize for that. Hopefully I've managed to cover most of your points. Kelly and I will try to reply by email to some of the remaining questions that you asked. And join us for our next webinar. I think the next one we're going to talk about dissipation tests. So I haven't yet really covered dissipation tests, about the theory behind them, how you do them, and how you interpret the data. And there is a little module in CPT that allows you to interpret dissipation tests, and so we'll show some examples on how you do that. So again, I apologize that we lost the webinar during the process, and hopefully it recorded okay. If not, we will redo it so that it will get recorded, and a recording of it will appear on the website. So thanks again for attending, and we'll try to answer the remaining questions by email.